Okay, y'all. So section 9.3, we're still in chapter 9, is no longer about proportions. Okay, so the first thing we did in this chapter was the t-test. The next thing we did was the z-test for proportions. So today we're talking about if you're interested in variance or standard deviation. Okay? Most of the time students don't have this in their FRP, this type of test, but it is still important, all right? So, inference is about the variance of a normally distributed population. Use the chi-square distribution. So, the properties of chi-squared is it is non-negative, which means you don't have a symmetric distribution anymore. It's not symmetric, okay? It is right skewed, so that's why you saw me draw a picture like this. Non-negative means the lowest value is 0, and then it's going to go on forever towards positive, okay? So chi-squared is not symmetrical. It is right skewed. It is non-negative, and it's distributed so that it forms a family of distributions. So you have a separate distribution for each different number of degrees of freedom. So you'll notice if your degrees of freedom is 1, it means you have a sample size of 2. That's terrible. And you'll see what the distribution looks like. When the degrees of freedom are 4, it means you have a sample size of 5, and you see that skewness. It's very skewed still, right skewed. When you have degrees of freedom of 10, it creates a mound shape, but it's still skewed. So we're starting to get more and more symmetric. And then when I get degrees of freedom 20, you'll see it is starting to look more and more normal. It's still going to be skewed, because this goes on forever this direction, but it approaches the normal distribution. It starts to look more and more like it, okay? All right, so I wanted to show you this because we have talked about on the normal curve, your mean, your median, and your mode are about in the same location. Do you remember that? On the normal curve, remember, your mean, your median, and your mode are all kind of in the center right there. Well, when it's the chi-square distribution, your mode is still the most occurring. So it's going to be that highest point. But then your median, that's the value that splits it 50-50 on each side. So depending on how skewed it is, you know, that might be close to the left or the right. And then the degrees of freedom are equal to your mean. Yeah, so I wrote some little notes for myself just to help me remember. Remember, mode means most, so that highest frequency, and then the median splits it 50% on one side, 50% on the other. And because it's skewed, that's not going to be exactly in the middle. Depends on the skewness, okay? And then degrees of freedom equal your mean. Okay. All right, so we again are going to be using our calculator to find the cumulative probability. So again, that's second. Then you hit distribution, so the var, second vars to get the distribution. This time we're going to choose chi-square CDF. And remember, I'm going to pause actually, let y'all write, and then I'll talk. All right, so we did this with the t-distribution, remember? But the t-distribution, the lower limit, which is what this is, remember the lower limit was negative 1e99. And that's because that distribution technically goes forever to the left, forever to the right, okay? But for chi-squared, it's non-negative, meaning the lowest value is 0. So that's why the first value is 0 here. That's your lower limit. That's the smallest it can be is 0. Then whatever you calculate for your chi-square, that's what you put second, and then still third place is degrees of freedom, okay? So it's very similar to the t-distribution. The only difference is the lower limit is your is 0 because we don't have any negatives, okay? That's literally the only difference. So if the area is in the right tail, then again we have to subtract from 1 because your calculator always shades to the left. So let's go ahead and practice it with this one. I do ask that you write down what you're doing. So just like before when we wrote t-CDF, now we're going to write chi-square CDF, okay? So chi-square CDF, open the parentheses. parentheses. My lower limit is 0. Then I'm going to put my chi-square value, so 20.2. And then I'm going to put my degrees of freedom, which was given this time, 15. So everybody in your calculator hit second bars, go down to 8, the lower limit 0, upper limit 20.2, and then degrees of freedom 15, and paste it. It gives you 0.835606039. So is that the probability if we're looking for that area to the left, a left-tailed test? Yes. So my p-value would be, my probability would be 0.836. I rounded. So if it's a right-tailed test, then I would need to do what? Yeah, so it's going to be 1 minus 0.8356, blah, 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 whatever that was. So while it's in my calculator, I'm just going to do 1 minus, and then arrow up and grab it. And I get 0.164. So the nice thing is your calculator always shakes to the left, okay? So if it's a left-tailed test, whatever value you get is the probability, is the p-value. If it's a right-tailed test, you have to subtract from 1. What if it's two-tailed? Just multiply by 2. Yep. Very good. All right, so this is the chi-square test statistic. It's chi-square star, and that's because if you print out the chart, you have chi-square values, critical values, to be able to compare chi-square star to them, just like we had Z and Z star, T and T star. So this is your test statistic. So it's n minus 1. N is still sample size. S squared is what? S is standard deviation, so if it's S squared, it's variance. This whole thing is variance. So if you're given variance, you just plug it in. If you're given standard deviation, you have to square it. Okay, everybody, do you understand? Let me say that one more time because y'all are writing. If you're given variance, just plug it in. If you're given standard deviation, you have to square it, okay? So this is the variance of the sample. This is the variance of the population. And again, just like with the t-distribution, your degrees of freedom are going to equal n minus 1. I like that that's the same too. You know, it's not like you have to learn a different one. Questions for me? No? Okay. So the soft drink bottling company wants to control the variability in the amount of fill by not allowing the variance to exceed 0.004. Does a sample of size 28 with a variance of 0.007 indicate that the bottling process is out of control with regard to variance at the 0.05 level of significance? So this is a real world problem, so you can see why sometimes you need a chi-square distribution. Okay? Alright, so what is my parameter of interest? This is super important because the more tests you learn, you have to figure out which one to use. Okay, so what am I interested in? I'm interested in variance. So I'm interested in sigma squared. Okay? Which is the variance or the variability variance in the amount of fill. So automatically my brain, because I see sigma squared, is like, boop, chi-square test. Okay? So now we're going to state our null and alternative. So, time out. If your parameter of interest is sigma squared, automatically what goes in your null and alternate? Sigma squared. And the bottling company company wants to see if it's out of control. Yeah, it doesn't say less than, it doesn't say greater than. It just wants to make sure it's not either of that. You know what I mean? They want to keep it around that same. And that makes sense, because if I bought one and my bottle was half full and you bought one and it was all the way to the top, and then that person bought one and it was somewhere in between, you know, we'd all be like, we paid the same amount. So that's important when it fills your bottle, that it's about the same amount each time. So we're going to put sigma squared, okay? And then actually, I underlined something, and that actually helped me. It says the soft drink bottling company wants to control the variability in the amount of filled by not allowing the variance to exceed. Does a sample of size 28, so that's a sample, that's n equals 28, with a variance of 0.007, so that's s squared. So exceed, what does exceed mean actually? Greater, so that's what they're researching. So actually my alternate's going to be greater. We don't want it to be greater than 0.0004. Which means we'll be okay with it if it's less than or equal to. Yeah. Sometimes I have to do that. I have to go back in the problem and look. And it helps me when I identify the sample statistics. So I knew that's what I'm testing then. Okay. All right. The hypothesis test criteria. Did you catch it from the page before? On this one, it says they want to control variability. Would you think it would have a normal distribution? Yes. What? Good. So the higher your sample size is going to start to approach the normal curve. It looks like it. So as long as your sample size is pretty large, and she's right, when I was drawing it, she's pointing to her sheet that looked like this. You know, as we got to degrees of freedom of 20, it looked pretty normal, didn't it? So as long as your sample size is large enough, we're going to assume normality. Okay, we're going to assume it. Because with chi-squared, it starts to approach the normal curve depending on the degrees of freedom. So for this one, because my sample is 28, 28 minus 1 is 27. So I'm going to assume normality because of the chi-square distribution and my degrees of freedom being bigger than 20. Okay, 20 or bigger. All right. So now we're going to write down our sample evidence, which I already wrote it because it helped me write my null and alternate. But we can write it again real quick. N was 28, and sigma square, which is variance, was 0.0007. So now because of that, we can calculate the test statistic, right? So that's going to be chi square star equals, your formula is n minus 1, so we're going to plug in 27, and then times s squared, so times 0.007, divided by your sigma squared. So what was in your null and alternate? 0.0004. Why am I not squaring those? Because they're already given to me as variance, okay? That's important. That's the one common mistake. All right, so now if we calculate it, what do we get? 47.25. So, using my calculator, chi-square Cdf, 0, 47.25, and then my degrees of freedom, 27. type that in, you get? Good. 0.9907. Yeah, it keeps going. So you ask yourself right here, and now, y'all, this is the exact same as what you've been doing. Left-tailed, right-tailed, two-tailed. Look at your alternate. Right-tailed. So what do I do? Subtract 1. 1 minus 9907, blah, blah, blah. And we get 0.0093. And now I can compare that to alpha. Yes, what was your question?
Well, I didn't know if it was really taking that much, but I got like 45.5 from my technique. I don't know what I did.
Uh-oh. No, I could totally have a mistake. I mean, I hope not, but you got a different test statistic?
Oh, never mind. I know what it is.
27 times
I thought
20.
you said 27 minus 1, so I copied that down.
Oh, no. I subtracted 1. I'm sorry. It's n minus 1, which would be 28 minus 1. I may have misspoke. I'm sorry.
Yeah, I had the same thing written down.
I sometimes solve it in my head, and because I'm doing that, it comes out of my mouth. I'm sorry. 27 is the final thing. Your sample size was 28. Let me double check. Yeah, 47.25. All right, y'all. I know that was kind of quick, but from here down, it's the exact same process as like the t-distribution. You know what I mean? And your results still have 3 parts. You still compare it to alpha.